Alright, this task is kind of the quintessential mathematician's task. When mathematicians come across a problem and they start thinking about a specific thing, invariably what they ask themselves is, what happens in the general case? And one of the things that mathematicians often think about in the general case, so in specific this sort of instance, is what happens if we have an arbitrary number of objects on our cards? We often in mathematics call that number n, but you know what? For students, I find it much easier to think about a specific value of n and then sort of think about how the problem works with that specific value and then notice that there's nothing special about that specific value. So you could think about n as 1,000, or you could think about n as 30, maybe the number of students in your class. Let me give you a little bit of a pictorial version of the mathematics that's going on here so that you can help prompt the students. It's kind of the same as what we did when we had lines that went through 3 objects. So, say we're trying to make classes with 30 students in them. Well, suppose we have Jill. Jill is going to be in a class. Alright, so here's one class that Jill sits in. Suppose we had another class that doesn't have Jill in it. Well, if Bob is in this other class, how many classes could Bob be in that Jill's in? Only one, right? If Bob's here, Bob and Jill, as soon as we have Bob and Jill in a class, we can't have another class with Bob and Jill in them. But wait a minute, so this class here has 30 students in it, and none of them are Jill. So we have Bob and Sarah and James and Joanne. And now any class that has Jill in it has to have one of those other students. But we can't have 2 classes that have Jill and that same other student. So the number of classes that Jill can be in is at most 30. She could be in the class with the first student, the class with the second student, the class with the third student, and so on and so forth. But as soon as Jill's in a class and Sarah's in a class, we can't have another class with Jill and Sarah in it. So what does this show us? This shows us that Jill can be in at most 30 classes. But now we have this first class that Jill's in, and there are 30 students in that class. And this same logic tells us that each of those 30 students can't be in more than 30 classes. But any class has to have one of these students in it. So how many possible classes are there? Well, there's 30 students, and each student can be in at most 30 classes, so that's 30 times 30 is about 1,000 classes. So if we have 30 students per class and we want any 2 classes to have exactly one student in common, but we don't want that always to be Jill, then at most we could have 30 times 30, which is about 1,000 classes. Now this gives us a good upper bound, but it doesn't tell us how many. We don't know that we can make almost that many classes. So we're going to see more of that a little later on. But for now it's nice to sort of know if we had 1,000 objects that we wanted to put on each card, well, each object could be on at most 1,000 cards, because remember, if we have this paperclip on a card, and we have another card out here that has 1,000 objects on it, none of which are this paperclip, then any card that has this paperclip on it has to have one of the objects from this card. And you can't have 2 cards that have the same object on this card and the paperclip. So there are at most 1,000 possible cards that have the paperclip on it. But now if we had one card that has 1,000 objects on it, and each object on that card can be on at most 1,000 cards, then how many possible cards can we have at most? Well, there are 1,000 objects, and each object could be on 1,000 possible cards, so that's 1,000 times 1,000 is 1,000,000. So if we have cards with 1,000 objects on them, there can be at most 1,000,000 different cards. Unless of course we have that trivial solution where they all have the same object on them. Alright, so in general, if we had a card with n objects on it, each object can be on at most n cards, so there's n squared possible cards. See how that works? You think about it with 30, it makes sense. You think about it with 1,000, it makes sense. And now all of a sudden, you can sort of extrapolate to n. I don't even understand how that works, but somehow or other doing 30 and doing 1,000, you see that there's nothing special about 30 or 1,000, and all of a sudden you see the same argument works for any number, and then we can just put in any number. Any number is called n, and all of a sudden n squared is an upper bound. Alright, see how your students go. See if they can get close to that. And if you want to sort of help nudge them in the direction, suggest to them that they have a card that has this paperclip on it, and they have another card over here that doesn't have this paperclip on it. How many cards could they have with this paperclip on it? Bearing in mind that they also have to have one object in common with this card, and that no cards can have two objects in common. Right, have a go. Let them brainstorm, let them wrestle with each other, let them spitball ideas. This is a good one for that.